The communist electrical system employs a forced oscillation. Here on this diagram we can see we got our primary over 2 to start off on the left, the primary and secondary for phase 1 and the primary and secondary for phase 3. Normally we would never make these interconnections, and in this system we seem to be able to make those interconnections and acquire a situation where VT for the total of the 3 inputs amazingly is over 97% of what they would be if these were all exactly in phase. Now we even encounter situations where VT becomes greater instead of less than the sum of its components, and hence we can say the whole is greater than the sum of its parts. We've gone over some of these things and made mistakes on the last video, and we're going to rectify those mistakes now. On each phase we have an amperage meter. An amperage meter there, an amperage meter there, an amperage meter there, and those are all left open connection. So if we want to, we can compare the total amperage derived from the communist system, where the currents are repressed and everything is collectivized. All the currents and all the phase angles and all the voltages are all the same on these 3 when you join them 3 to provide a load to VT. In contrast, we have amperage meters that allow to show us what can be obtained if instead the free vibration method was employed, and P2 takes its energy from its secondary, and each one does that. Not in unison, but separately and individually empowered from the phases that the coil sits atop, or below in this case for phase 3. Okay then, so my friend comes by and says, well, you know what, when we do this, we put amperage meters in all 3 phases and see the total amount of vibration that we can get from a 5-volt stator or so. We get about 4 amps, and in the communist method we only get less than 3 amps, but we're going to show all that. First we got a paradox in that where VT becomes greater than the sum of its components, and that happens when you put an amperage meter on all 3 of these oscillations and also measure VT, which is the total of that series chain. Since we're not extracting energy from that portion of the circuit, these 3 can vibrate independently, and when they're shorted, their voltage measurements will go down to close to 0. And my friend said, well, no, what you're doing is wrong, is you're not accounting for the internal impedance of the amperage meters themselves. Okay, I says, this is new to me. He goes, what you need to do is short out each V2, V1, and V3 with alligator clip wires, and that's what I did, and I got a little bit of different result, and we're going to go from there, turn the thing on, and look at our amperage meters. Let's start out with our voltage meters then. These are all going to be reduced down to 0 now completely, because we only have an amperage across the voltage measurement as a meter short, but also an independent alligator clip short. So what we're really going to need to do is to show, let's turn it on first of all. This is the motor and 3-phase alternator, and we're going to be able to see how much energy goes in the field when we turn it on. Right now the field's not turned on, as evidenced by the 0 reading. We got 3 alligator clip wires shorting everything out. Those top 3 meters should be reading close to 0 volts. And right now we're getting just about 0 volts out. We got 0.03 of a volt on the end meter. And every everything's pretty much zero across the line. Maybe our friend's right. Okay, even though everything's zero across the line, we assume that all the amperage is going through those extra shorts we placed on there. We find out that the amperage meters are still reading amperage. So now one at a time we can reconnect that amperage. You'll notice the camera viewpoint is going to be very good. Let's try to get a better camera viewpoint. There's our 3 amperage meters, and we're reading 0.05, 0.08, and 0.02. Now we're going to go and remove the short across 02. And that went up from 0.02 to 0.18. Short across phase 1. That went up to 0.44. Typically, that's going from 2 to 1, and we find out that, well, that's beside the point. We'll go ahead and energize all 3. And that's what we got on our zero field amperage. Go back and we look over here. We're cutting something different today, I guess. I don't understand all this either. We got 0 and 0 and 0 volts summing 0.17 volts. Not a very convincing demonstration. Now we want to go on and try to get to the more convincing demonstration. We're going to go ahead and turn our field on. See, something fell back there. And show what it takes to get a 5-volt field on the phone. Showing 2.7 volts, enabling 0.56 amps. I don't know if we can see that. Now we can look in the actual field. We've got about 4 amps, free vibration. We're going to look at our voltmeters. First of all, we're going to unhook the left and the right amperage meters. And since we now allowed the that middle coil in the series, where's my pointer at? That middle coil in the series over phase number 1 is now at near 0 volts. Point 2. We got 3.2 and 3 volts on each adjacent coil, and we have a summation to 7.47, 7.5 volts, and our draw on that phase is 1.9 amps. Due to the 10 limitation, we're going to have to shut down.